Friends, welcome to my YouTube channel. Dhanesh here. So in this video, I am going to discuss about the fully connected layer of convoluted neural network. See, we have discussed about convolution layer, ReLU layer, max pooling layer. These layers we finished. See, convolution layer. I already discussed convolution. It's a mathematical operation. Here we combine two functions to a third function. In our case, we combine the image and the kernel to produce a feature map. That's what we do in the convolution operation. Why we are doing this operation? Because when we take an image, it can be deformed on, or if you take an animal, or for example dog. So in that species, different animals little bit look differently. So all these identification how we can do, so that for that only we use the convolution operation, convolution algorithm we have discussed in the previous video. Now for the second layer, ReLU. So if you ask me what is the purpose of this ReLU function, it is it is used to introduce nonlinearity in the neural network. Here in CNN, we used to learn nonlinear function. Most of the functions we are analyzing is nonlinear. So we are going for a ReLU function. Then you will be getting a doubt, why can't we go with sigmoid or hyperbolic tan? They are also nonlinear. The advantage with ReLU is it's having a high level of saturation. If you analyze hyperbolic tan or sigmoid, their saturation level is less. And for max pooling, why we are using max pooling? It's for shrinking. So it's for shrinking the output of the ReLU operation. We are shrinking to a smaller size by using the max pooling layer. So all these operations we have discussed. So today I am getting into the fully connected layer. So in this video I am going to discuss about fully connected layer. Fully connected layer in artificial neural network. See, before getting into the fully connected layer, so you may be aware, the output of the ReLU operation, we got a 4x4 matrix. With this is the map we got. Its size is 4x4. See, we have started with a 7x7 matrix, and it's changed its size to 4x4. Now what we do is we stack up all these layers. We will do one more convolution, ReLU and pooling. See, what we are going to do is we will repeat this operation. See, first time we have done convolution, ReLU, then pooling, max pooling. This we have done. Again, one more time we will repeat this process, convolution, ReLU plus pooling. One more time we will repeat. So here you got a 4x4 sized map. Then here you will again, it would be shrinked into 2x2. So this is the output. See, we stack up all these layers, convolution, ReLU, pooling, and the 4x4 output, 4x4 map becomes 2x2. So this is what we are going to give it to the fully connected layer. So you understood this. Now one important point you need to understand here in fully connected layer is the input layer of the fully connected feed-forward network is fed with flattened data. Very important. So what we are giving here is flattened data. That is the one important point. Fully connected layer means the fully connected feed forward network. Here we are using the fully connected feed forward network. That's the to that fully connected feed forward network, the data we are giving is the flattened data. So what is the process of flattening? So next I am going to give you idea about the process of flattening. So what is flattening? See, flattening collapses the spatial dimensions of input into channel dimensions. So that's what flattening do. Flattening collapses the spatial dimensions of input into channel dimensions. See, here we take the shrinked image of the max pooling layer and put this into a tensor known as vector. So we have, the shrinked image from the max pooling layer. See, in this, convolution operation and, all the previous operations, we used three filters. You remember that I told you can use any number of filters. So the more the number of filters, the prediction will be, the accuracy will be high. So we used three filters, and the output we got it from these three filters. See, let us assume that this is the output we got from it is a 2 by 2 matrix, 2 by 2 map. So this is the three outputs we got it from this. So this is, you can put it as 1. This I am taking it as 0.5. Here it is 0.5. Here it is 1. Here it is 1. Here it is 0.5. Here it is 0.5. Here let's assume some arbitrary values. 0.5. Here it is 0.5. So you know the calculations how it is you are getting it. So you can see that. See, here it is 1.0 and here it is 0.5. So this is the values we got it from we have done 2 levels of convolution, ReLU and pooling, and finally we got into 3 2 by 2 maps. So what we are going to do is all these values we are putting it in a tensor known as vector. See, in this we are putting all these values into a vector. See how we can put it. See, we are putting it into a vector. This is our vector. So this is the vector. So I will put the first one 1 2 3 4. So we need 4 to 3 12. So 1 2 3 4 5 6 7 8 9 10 11 12. 1 2 3 4 5 6 7 8 9 10 11 12. So I am arranging these values. You see, 1, the first one. Next is this 0.5. Then this 0.5. Then 1. Then we will come to the second one. The second map, it is again 1. I put it here. Then again 0.5. Then you have 0.5. Then you have 0.5. Then here you have again 0.5. Then 1.0. So we will take it like this. We will we will first this, then this, then this, then this, like this. 1.0, then again 1.0, then 0.5. So we put all these values into a vector. This process we call it as flattening. This is very important. Even if you use the libraries like Kera and all, the tools like Kera and all, there is libraries to handle this flattering operation. So this is the process known as flattening. See, this flattened data is given to the input of the fully connected layer. So this is one thing extra we are doing. So this flattened input now we are going to give to the fully connected layer. That's what I am going to explain you now. So the fully connected layer, the fully connected layer, you have this is what it's usually happen. You have the input x1, x2, xn, like this. This is x1, this is x2. Here you have the hidden layer. So here we call it as the fully connected layer. Instead of hidden layer, we call it as the fully connected from a convolutional, in a convolutional neural network. This hidden layer we call it as the fully connected layer. That's another point you need to understand. And here you will be having multiple outputs for classification. Let's have two outputs. See, this is, all are connected, interconnected, by using, just 1 second, we will use the, you know, black for the weights. This represents the weights. This is connected, interconnected. Here also it is interconnected. This is connected, this is connected, interconnected, and here it is, again it is interconnected by using the weights. Sorry, so this is the wrong, sorry. You have this, then you have this, you have this, you have this, again you have this, you have this. So these are all the two outputs. So we will take it as one. So this is the, this is known as the fully connected layer. The hidden layer, here we call it as the fully connected layer. So the one important point is, to this fully connected feed forward network, we are feeding the flattened data. I told you it's there in a in a vector. We have this flattened data. Now, so the real classification, see, the exact classification happens in this fully connected layer. This is very important. The actual classification happens in the fully connected layer, and we have, if you see the output, you have multiple neurons in the outputs. That's very important. You have multiple neurons for classification. See, when we analyze the vector, see, I have, I have shown you the vector previously. So if you analyze the vector, there are certain values are high for X. And when we repeat the same process for another letter Y or A, certain other values will be high. See, I can show you the vector once again. See, if you see the vector, you can see it, I have written previously. This is the vector, you got it. If you see this vector, this was the vector. It is like 1, here it is 0.5. Let's assume some value, 0.5, here 1, then again 1, then you have 0.5, 0.5, 0.5, then you have again 0.5. The space is not here, I am writing it here. See, you have again 0.5. Then you have again this is a single vector, you please understand, it is a single vector 1, and here it is 0.5. So this is a single vector, it's a continuation here. You have to understand that. So if you analyze this vector, this is a single vector. See, this value is very high. This is 1 is high, here it is high, and here it is high, and here it is high, here it is high. So it is the first row, then first row, second, third, fourth row, then the fifth row, then 6th, 7th, 8th, 9th, 10th and 11th. See, these values are high. So from this, the letter X can be identified. For when you do this convolution, convolution algorithm, ReLU and max pooling, and finally come up with an output in the vector after the flattening operation, these specific values are high. From this, we need to understand for X, these values are high. For another letter Y, if you take, some other values will be high. So this is the, way the classification happens. Based on that, so the when we analyze the vector, there are certain values are high for X, and when we repeat the same process again, convolution, ReLU, and all these operation, max pooling, everything, flattening, certain other values will be high for another letter Y or M or N. So the here, by using this values, the fully connected layer does the classification. See, the real classification you need to understand the training is to be done. So for our model is to be trained. So here how we train, how the training is happening. You know, for a fully connected feed forward network is trained using back propagation algorithm. You know that the fully connected trained network, it is the training is done by back propagation algorithm. You know that you are familiar with this algorithm. This is the most important algorithm. You need to learn it. So it is trained using backpropagation algorithm. So backpropagation is a supervised learning algorithm for training neural networks. Here we will update the weights and biases using gradient descent until the loss function is minimum. You know this algorithm. So we use this backpropagation algorithm, and we trained our fully connected network, our convolutional neural network, such that now our network know this is X. If you give some value, see whatever input it is having for the X in our other trained model, this is X. Now if I give another value for X, again the same process it will repeat and come up with a vector like this and compare that vector with this vector. So for the trained of convolutional neural network, this is X, this is the X. Now if we give a new value for X, so we are giving a new value for X. For example, whatever value I am giving now, it is, let's assume that I am giving an input image, and for X, and the same process it's repeated, the same process it is repeated, and this is the trained data, it's there in the CNN. Now I have given a new image, new input image I am having. So the new input image, it's processed, all the operations it's done, convolution, ReLU, max pooling, flattening, everything it's done, and finally our network got these are all the values it has to compare. Yeah, so got the values, it is 0.9, then it's having 0.65. Let us assume some values, then again 0.5, then 0.96, then again 1, then again 0.5, then again 0.55, then again 0.55, then 0.55, then 0.9, again 0.9, then 0.5. So these are all the maps. This is the vector, it got it for the new input image. That's what we are using for prediction. So this is the map it's got, this is the one it's got. So this see which layers only, what are the rows for X, what are all the rows it's checking. It's checking the first one, then the fourth one, fifth one, 1 4 5, 1 4 5 6 7 8 9, then 10 and 11, 1 4 5 10 11. These are all the values it's checking for X, whether it's high or not. So here we have the first one, 1 we have taken, this is 1, then you will check this one, then you will check this one, then again these 5 values it will take. So when you sum all these values for the trained data, when you sum it, what you will get, it is 5. So when you sum it here, you will getting it as 5 here. Here it is 1 1 1 1 1 1 plus 1 2 2 plus 1 3 plus 1 4. So these are all the values, you know it. So when you sum all these values, this one, this one, this one, and this one, when you sum it, you will get 5. So this is 5. Now we will divide. So here you have, when you sum 0 0.9, 0 0.96, 1, again 0 0.9, 0 0.9, almost you will get some range. It's around 4.57. So the answer from this, it is, you are getting 0 0.91. It is somewhat near to 1. So this is 0 0.91. Then if you give another letter and showing it as x, again it will take the values for another letter you have given. The values are like, let us assume like it is some different values. Sorry. The different values. This one is 0 0.4. This one is also sorry, this is 0 0.5. This is 0 0.5. This is also 0 0.5. Let us assume that those values, you have shown another letter y. So let us assume that the values we are getting, it is different here. So here here you are getting it as the first row, you are getting it as 0 0.5. Here you are getting it as 0 0.5. Here also it is not 0 0.9. It is there also you are getting 0 0.5 and 0 0.5. All the values you are getting, let us assume that it is 0 0.5. So when you add it, and what you will get, it is it's up 0 0.5 plus 0 0.51, then 1 plus 1 2, it will be 2.5. so this 2.5 divided by again 5, this will be 0 0.5. so this 0 0.5 is less than 0 0.91. So 0 0.91 is a higher value. That means this the second one, whatever I told, is not x. The first one is the value x. So you got the point. See, this is the trained value, the convoluted neural network. After the backpropagation algorithm, it's used and it's trained, and this is the vector it's having. So when we give an input value, it will add all those values, the corresponding place, 1, 2, 3, sorry, 1, 4, 5, these values. These are all the higher values, 5, 6, and these values it will add. And here also it will add, and that value it will calculate. It got 0 0.91. The second case, again, it will check the corresponding higher values. Here it is 0 0.5, 0 0.5. When you add it, you will get 2.5. Again, divided by the sum of these values, 5. That is 0 0.5. Here 0 0.91 is higher than this 0 0.5. So the first image you have given is x, and the second image you have given is not x. So this is the way it does the classification in fully connected network. So thanks for watching.